Thank you. I think we ought to be close enough to starting. Welcome back, everyone. So now it's week 8. We're on the midterm week. I know it's a pretty busy week for a lot of us, but our week is going to be kind of light. Our goal is to finish off section 5.4, and then we're going to do a 2-part review. We'll be reviewing on Wednesday's class as well as Thursday's class. And at least, although it's a busy midterm week, our exam is only going to be on the week after midterms. So exactly a week from today. It's going to end on section 5.4, which we're going to be finishing up really shortly. And it begins in section 3.4, dealing with box plots. Well, any questions, folks, before we get started with our work today? Okay, well, let's finish up our problem that we left off on in section 5.4. These notes are pretty long, but not as bad as 5.3. 5.3 had lots of different concepts, and this one's a little bit more directed, just conditional probability. So what goes on in conditional probability? Well, let's take a look on the problem we kind of left off on. The context of this was we have 626 participants in a study. Some of those participants have hepatitis C, some of them do not. Most of them do not, that's good. Some of them had a tattoo done on a parlor. 61 of them had a tattoo done elsewhere, and 513 of the participants had no tattoos. So given all this information, well, it's a two-way table since we have data going in columns, data going in rows. And now we can start asking and answering interesting questions about how are having hepatitis C versus tattoos related. We're not trying to say one is causing the other. So what we did on our part B here, to find the conditional probability of having hepatitis C, read the vertical line right here as given, no tattoos. Really all we did was we took the table and we got rid of all the possibilities except for having no tattoos. So this right here told us focus right on that row. That's really our whole sample space, the 513 participants. So we put 513 in the denominator and we got our probability in really pretty fast order from there on out. But really the idea is, if you look at the given information, it tells us to focus on either a row or a column. And it's also telling us where our denominator is going to turn out as we do these kinds of problems. Any questions at all, folks, on getting through part B? Okay, well, let's forge ahead. Let's try out our brand new problem. Part C was so same scenario. And the table we're dealing with is just pasted here for easy reference. That way we're not scrolling up and down a whole bunch as we solve these. Could probably make it a little bit bigger. Part C is asking us next, what is the probability that a randomly selected person has a tattoo, not done at a parlor, so that's very specific. That'd be tattoo done elsewhere we're taking a look at. Given that this person that we're given is a huge, huge buzzword, so let's color code that, does not have hepatitis C. That'd be C complement, so we're dealing with this column right here. So that's probably how we'd start this off. Always a good idea to write down the probability statement. So if that comes up as the question, we'll know what the meaning is. So I'm going to write, what is the probability? Tattoo not done in a parlor is tattoo elsewhere. So let's go TE for this person has a tattoo done elsewhere. The given right here, we'll just put in a vertical bar to represent it. And does not have hepatitis C, we put in as C complement. Sorry, talking's hard today. Okay, I think we've got it, folks. Now, it's all about that given information. You always want to focus on what is given, or the second position, right where the red dot is, inside that probability statement. When it says given C complement, it means effectively, all this stuff has no bearing whatsoever and what we're about to do. So we just completely delete it. Does that make sense to folks? Okay, so now we're just talking about hepatitis C, folks. That means our denominator is going to involve the 579 participants. In fact, it might not be a bad idea to remove this column right here. So I'm not worried about that total that was right where the red dot was, because it's this total that now matters in this problem. So given hepatitis C, we count the number of ways a participant could have hepatitis C, just 579. We didn't really count them, we just grabbed them from the column total. And anyone see what ought to go then in the numerator up here? Exactly, tattoos done elsewhere, or not done in a parlor the way they wrote it, is just the 53 outcomes right here. Now, you don't have to have a big black marker to do these problems as a quiz or an exam problem. Sometimes a couple like blinders, like a note card or something is helpful. But this is pretty much the whole method of doing this. Let's throw it into a calculator and get a result out. So it'll be 53 division by 579 participants gives us a probability. I think this one is to 4 decimal places. So 0.0915. If I copied those in correctly. How does that look to folks so far? Awesome. So it's saying altogether, we have a 9% chance that something happened. Well, this problem is kind of nice because the question is really the interpretation. There is a probability of 0.0915 that a randomly selected person has a tattoo done at a parlor, given that they do not have hepatitis C. But again, that's kind of a tough interpretation in all honesty. Let's do another one that goes like this. Using the orange pen because this isn't required, this part's optional. It didn't ask for a practical interpretation. But another way to think of this is we can say that there is a 9.15% chance that, then go inside here, and let's say that among, starting to not like this sentence. Let's do a do-over on this one, if that's all right with folks. We can make it work, but it's going to sound broken. Let's make it a little bit more grammatical. I want to focus here first. I think that's where I lost my way and try writing out that sentence. Let's say among all participants that, then right here, let's just say do not have hepatitis C. Do not have, I'll abbreviate hepatitis to just hep, so hep C. Now, next thing to look at, I'll say the probability as a percentage chance. So among all participants who do not have hepatitis C, there is a 9.1% chance that a randomly selected person has, then I'll say right here, a tattoo done elsewhere, meaning not in a parlor for our organization. So has a tattoo done elsewhere. So that's the interpretation on this one. Again, kind of tricky when we're dealing with this. It's not a bad idea to say, if you like this kind of approach, 9.15% chance of having a tattoo done elsewhere, given the person doesn't have hepatitis C. So you can always just read it left to right if you prefer. But I feel like a lot of people say those interpretations are just as confusing as the probability statement. So if you feel like that's confusing to you, this is just another way to write out that information. Well, any questions, folks, on running through this one? Okay, as you study these kinds of problems, think of what we're doing with these black bars as not something that's required. We may not do it on the next problem, but it's mostly just a guide. If it says given C complement, all of your data is right here on the column. And if the problem was saying given N, not having a tattoo, that's why we wiped out everything except that one row. All of our data lived in that region instead. Well, I have a couple more questions along these lines, really just practicing dealing with conditional probability and also how it connects with another topic, independent events. But any questions at all, folks, before we try that other topic? Okay, before we take a look at it, let's refresh ourselves on independent events because that's tricky on its own. We did two basic problems when we're just trying to break down that definition and get used to what it was trying to communicate to us. And that's these problems right about here. Here they are. So when it came to independence, let's focus maybe on just independence itself. It's about whether an event occurs or doesn't occur if our probabilities are affected. So here we said A was getting a tails on our first toss, B was getting tails on the second toss. But as a class, we decided the probability of getting tails would not change whether A occurred or didn't occur. This is what we might have said if we had conditional probability. The book was organized differently, but in the view of conditional probability, here's what we would really have said. The probability of, let's call this B, given A, so there's a lot of colors, I probably should have thought that ahead. Probability of B given A just came out as probability of B. So what is this saying? Well, the given A is saying A has occurred, or potentially that it has not occurred if we put in an A complement. So the probability of B, given that A has occurred, is just the probability of B. This would mean A occurring or not had no bearing whatsoever on the computation of probability of B. This didn't happen to us at all. Our probabilities were different. Let's take a look at them. When we, for example, did the probability of C right here, we got a 7% chance. But probability of C having hepatitis C, given no tattoos, well, if you didn't have tattoos, it went down to about 4 1/3% chance. So that means these are dependent events. Having hepatitis C is dependent upon whether we know this event occurred or didn't occur. So that's the idea of what's happening right here on the notes. Let's take a screenshot of this just for a reference. And the new information is this right here in yellow. We can clear that off. These borders here always mean the problem is ended, and I deleted it. And here's just the new information we were discussing. And eventually, here's our definition. Well, not a definition this time, a theorem coming up now. Well, referring to what we were saying earlier, we have a notion for independence. We have a formula, but this is something you can use as a test for independence. So let's think of it in these lines. This is a test for independence. What I mean by that is when we first saw independence in section 5.3, there's essentially two style questions. One of the questions, same as in WebAssign, just says your events are independent. So now you know you have formulas on the table that you can work and navigate through the problem. Another question was a scenario where it's plausible that they would be independent. But this theorem is a new idea. Sometimes we'll be given information and they'll just ask us, does it look like it's independent or not based off the scenario? That's where we would use this test for independence right here. If the probability of E given F is still just the probability of E, we'll say F had no bearing on the probability of E, so it's independent of E. So that's a really fine equation for testing independence. Any questions, folks, about that equation there? Okay. Lovely thing about this equation as well is that's the last equation in all of chapter 5 we're going to cover. So congratulations, folks. We've made it over the hill, I'd say, on dealing with these kinds of problems. Now let's see how this problem goes together, or this theorem goes together with the example 2. So we have another table. This one's completely filled in, and it says the accompanying data are from the article Characteristics of buyers of hybrid Honda Civic IMA, preferences, decisions, process, vehicle ownership, and willingness to pay. The last one seems to be the big punchline for them, willingness to pay. So this was from a 2006 study. And they said here, each of these 311 people who purchased a Honda Civic was classified according to sex and whether the car purchased had a hybrid engine or not. So we have events, male, female, other events, hybrid engine, not a hybrid engine. We could just leave it in ordinary words if we'd like, but sometimes it's just a handy shorthand to do this. I'll consider this event as M for male. We could call this one M complement for not male, or just call it F for female, might be just as easy. We'll call this one H for hybrid. This one H complement for not hybrid. That would definitely make more sense here, less symbols this time. And we have a table total of 311 because of the 311 participants in the study. So it goes on to say, a randomly selected person amongst those 311 is to be selected. And now we have three different events. We kind of already indicated them. M is we selected a male, F is we selected a female, and H would be we selected a hybrid engine in that Honda that was purchased. That's a lot of information just to start a problem. Our formula is up here, but let's carry it down so it'll still be in view in a moment. Well, any questions at all, folks, about the context? Okay, so example 2, we'll practice calculating a couple conditional probabilities. And the focus this time is also giving an interpretation based off the context. This time we don't necessarily know what we're calculating. If it runs like this, we have to think about it and write it out. So it says calculate probability of H given F. Let's take this right here. Actually, I don't think we need to copy it. That's pretty viewable, I think. So probability of H, just throwing the color coding on this, given F, first thing we have to decide is, what's our denominator on this thing? Has anyone spotted what should go down below? If we're not sure, here's always what's a great idea. Grab a note card. I mean, your note card could look like this. Oh, I didn't mean to put notepad on that. So grab 2 note cards and just kind of go like this. So if it says given F, essentially all of your information is right here. So pretend those are real note cards. And, well, there is 117 different ways female could be selected. We're doing equally likely events, so all the participants had an equal chance of being selected. So that 117 just goes right to the denominator. Does that make sense to folks on where that 117 comes from? Awesome, let's throw these down. We don't want to save that one, and I should probably unhighlight that. That's going to be a little bit confusing. And just for the sake of reference, let me do one of those little screenshot things, just in case you come back to these notes. I want to know, how did we get that denominator? So just ignore this part right here, it kind of copied in. But we'll grab these counts right here. That's the 117. Now, probability of H is essentially the question. We want to know, how many ways did we get a hybrid engine? If all we care about were the female buyers, anyone see those number of purchases for the numerator now? It would be the 34, exactly. So this count of 34 comes from, I should use blue right here. Right here, at this stage, we're just about done. We're going to get a number, and then we just have to interpret that computation there. So we took the 34 females, Going into the numerator, we divide by the total number of females in the study, 117. And that's how the conditional probability is going to go essentially each and every time in this course. So let's go calculate this out. 34 of 117, that's definitely a weird number. And we have a value of 0.2906 after rounding to 4 decimal places. So now we're ready for the fun part. We'll give a practical interpretation and then we'll move on to the next question. I'm going to get into this style where whenever we do a practical interpretation, I'll copy the text, maybe make it italics to know that this is our work right here, and just put it right down here. So it's immediately apparent where that part of the work was answered. So for a practical interpretation on this one, we're going to do this twice. So I want to show both of the styles on both problems. So one style of a practical interpretation is just state the probability, read left to right inside the probability statements right here, and that will always qualify for full credit. So it's kind of a nice way to go. We'll say here, there's a 29.06% chance. Now we need to talk about what's really happening here. They're randomly selecting a purchaser of a Honda car. So I'll say here, randomly selected. Honda purchase. So now let's go inside the probability statement. We'll say here, the H is referring to a hybrid engine. Follow the arrows down below right here where we set our H. So say the randomly selected Honda purchase was for a hybrid engine. All we're now doing is just saying what the symbols mean. And when you see that bar, anyone recall the word we have to say right there for that bar? We could just say given if we wanted to, absolutely. So what I'm going to try to do with this problem is, let's use the given on part A, but on part B, we'll do the different style of interpretation. So we can kind of see what they both look like and maybe get a better idea of what they even mean when they say given. I feel like that's a confusing word just on its own. So if you say given right here across a vertical bar, I'm always completely happy with that for a practical interpretation. So given, let's use a good color though. Given that. And now we can say F is for female, just briefly, the selected person was female, or the purchaser was female. Given that, the purchaser was female. So that's what they're saying altogether. Or another way to think about it is, if you only look among the female purchasers of this hybrid car, 29.06% of those purchases resulted in a hybrid engine. Whew, we did it, folks. That's the practical interpretation and the probability computation right above. Any questions at all before we try it all over again? Okay, let's give this a new try. So probability of H given F, 29.06. Now we want to know the probability of M given H, and then interpret it at the same time. So let's see how this one ought to go. Let me clean up this table a little bit, and then we'll take a screenshot of this one, just to show where all the values are actually coming out of. So new computation. This time we want probability of M given H. So let me just rewrite it so we can focus on it as we calculate. Probability of M, that's standing for male, given. The given bar means we're essentially taking our sample space of 311 participants and we're reducing it down to only the participants that, let's see, corresponded to the hybrid engine, that event H. So here's probability of M given H. At this stage, I really haven't done anything, but at least in writing this down, we're thinking about it as we go through the problem. Let's use the black pen this time again. When it says given H, another approach is, instead of trying to find the right number here, you can black out the numbers you don't want. You could put, say, an X on it or something. I would only do that with pencil if it was an exam setting. But given H means we don't care about this one. We only care about H. That means we don't even need the column total going this way. All of that could be just completely eliminated. All of your information is right here. In a certain sense, conditional probability is nice because it's reducing your whole problem to just that. But the trickiness is knowing to reduce it to this. Then, well, H stood for having a hybrid engine. There's 111 of them. So we'll grab this count right here. We want to know the probability of a male. Well, there's 77, so we'll grab just that 77 from right here. So 77 goes up above. Now all we have to do is crank that one out and give an interpretation. Any questions at all, folks, on getting that 77 111ths? Okay, if we're happy with that, let's see what that comes out as. Definitely over 50%. So 77 divided by 111 gives us 0.6937. Now we want to give an interpretation to this one. And here's how it's going to go. Like we did before, you can just read it off, state the probability as a percent, and go left to right. H given F, just say what your H is and your F is, and that will always qualify. I consider this one to be kind of a fancier interpretation. It's not required, but people seem to like it only because I think it's easier to understand. That's the big takeaway with this way. So this time we'll say, among all participants where the event H actually occurred. We have to say this as a practical interpretation and say what H is. So we can say it this way. Among all Honda purchases with a hybrid engine, so I started with the given H. Now say the percentage chance. There's a 0.69 or a 69.37% chance. Sorry, I was struggling with the decimal point on that one. Move 2 places to the right. There is a 69.37% chance that something happens. Well, we said amongst all the H's, 69.37% chance that we go to the only event that we haven't talked about, and we'll say the purchaser is male. Finally, that solves this problem. We have a probability, and the hard part is always the practical interpretation right here. Well, any questions or comments at all, folks, on getting through this one? Okay, so this is what conditional probability looks like. I feel like it's pretty tricky once you're first learning it, but if you go through these notes again to get a feel for this, then it's directing you exactly where to look on the table. Also, our upcoming quiz number 8, I'll do one of these problems like we're seeing here, conditional probability. And so that will be kind of an extra hint on what is it going to look like on exam? Pretty similar to what we're seeing right here on these couple problems. And you'll get a feel for how to do it right before the exam. And just like with before exam 1, if you turn in your quiz 8 early, I'll grade it early as well so that you have the feedback on that ahead of coming in for the exam as well. Well, we have one last question, but any comments or questions so far, folks? Okay, so we've been dealing with these hybrid engines, Honda engines. Let me delete this table here. And now they're asking this question: are the events H and F independent or dependent events? And we definitely have to explain our answer on this one. But the explanation is not like a wordy explanation of the plausible reasons it might be independent or the plausible reasons might be dependent. It's more, we have to do something based exactly on these numbers we see right here. That could be kind of tough, but that's where this theorem that we copied and pasted right down below right here finally makes its entrance. If you're ever asked this question, are they independent or dependent events? You're probably going to be using this theorem right here, where the red dot is apparently permanent. So we need to calculate two things. Let's do probability of H given F. That's the left-hand side right here with the actual events we're using. We need to find out what that comes out as. And we also have to calculate the probability of H and find out what the value is for that one. That'd be considering the right-hand side where it says probability E. Now, the good news with this is, if you see this as an exam question, you may or may not have to calculate probability of H given F. Just take a look at the computations we've done already. Let's take a look up above. Probability of H given F. You can cite prior work on an exam, so let's just put in 0.2906. If we calculated it once, you don't have to do it again. 0.2906. So that's placed in. Probability of H is not terrible, but it's definitely going to have a different denominator. If we're saying just probability of one event H, then that's amongst the 311 participants in the whole study. That's our new denominator this time. H is having a hybrid engine, so we go to this column. We'll grab the total of 111 for that numerator. So now we have two probability statements. I don't know what 111 311s come out as. It's another weird number. So let's find that one out. So 111 311s comes out as 0.3569. I know these are close, right? Probability of H when F occurs is 0.2906. And the probability of H itself is 0.3560. So 35.6% of the participants in the study purchased a hybrid engine. But hybrid engines purchased only amongst the females came out to 29.06% of participants. So now this is basically a three-step process. Here's step one, do the conditional probability like here. Step two, do that conditional probability, or that one's not conditional, do that ordinary probability right there. And this is the easiest part to miss. Step three, don't forget your conclusion. We have to make an assertion, either they're independent or they're dependent. But let's take a look at what's happening. The probability of H given F is 0.2906, but the probability of H alone is 0.3560. We can say here, since probability of H given F is not the same as probability of H, the events are, anyone happen to know what it should be in this case? Is this independence or is this dependence? I think you're thinking of for dependent or straight up zero is maybe probability of A intersect B always comes out as directly zero when A, B are mutually exclusive. So if A and B couldn't occur together, that's a time when they just immediately come out as a zero in an intersection right here. But does that make sense on that question there? Gotcha. What's happening on this one is, let's go, we want to use a formula here, but let's go back once more in 5.3 to just get a feel for this. In 5.3, if we had the probabilities came out exactly the same, whether H occurred or didn't occur, if that happened for us, we would have said, yeah, we have independent events because B in probability wasn't influenced by A at all. It was always the same. But now for us, probability of H is either 35.60 as a percent chance, or if we know F occurs, it's influenced by F. It drops down to 0.2906. in a certain sense, would you all agree that this implies H actually does depend on F, whether it's occurring or not? Because when we said given F, it fluctuated the probability. Does that make sense in those kind of terms so far? Let's see if we can put this on paper. That's always going to be a little bit easier. We're going to need another page here. Actually, that should fit. It just looked like it didn't. Well, we'll move that up in a moment. So I think a good way to say this is, since probability of H given F is not equal to probability of H, the events are independent. But here's the additional information about this that I wanted to put down on paper as well. If probability H given F is directly equal to the probability of H, then H did not depend on F occurring or not. But that's not what happened to us. If we have not equals right here, oh dear, I made a mistake here. I should have said dependent on this. Sorry about that, folks. I think we were saying it, but when I went to write it down, I got it backwards right there. That would have been a -3 points or something like that for me if that was an exam question. They depend on each other, so they should have been dependent right here. Sorry for that confusion right at the last step. Let's add additional notes right down here, just to say, if probability of H given F is not equal to the probability of H, now that's what's happening to us in our current problem, then H is influenced by F occurring or not. So in this case, we could say this means H does depend on F. So here's the grand punchline to all of this. If you found equality when you compared the conditional versus the ordinary, equality here will always mean independence. But if it happened like it did on our problem, if there's just no way that these match, we're rounding to 4 decimal places. So if there's a mismatch to 4 places, not equals right here, like what happened to us, this will always imply dependence. And for rounding to 4 decimal places, it's kind of wild. I'm going to fix this number right here, so please don't copy this in. But even if it came out as 0.2907, and we're rounding to 4 decimal places, we'll consider these distinct values and still not equal. They're still going to be dependent in this case. They have to be fully equal into the precision that we're actually rounding to on these problems. So I feel like this is a pretty tricky question, but the formula right here is the main thing that guides us. 2 things will happen. Equality means independence, and inequality would always mean dependence. Well, any questions, folks, on getting through this one? Okay, definitely a weird kind of a computation. And it's weird because we've used independence before, but this time we're not using it in any probability computation. It's just a further up question about the nature of having hybrid cars or not, and gender as well. Well, let's turn up to the next example then. I'll leave this just on the top. So I'm leaving it here, but it's available on the top of the notes. That way the notes don't get too messy if you come back to read them. Here's what that problem ended. And here's our last example for section 5.4. There's a lot of reading on this one. And if you're not a sports person, No worries, we'll still break it down and see what's going on. And at the end of the day, it's all about what happens right here with these probabilities. I brought this question to class today because this one is definitely based off a web assigned problem. So you will see something like this one in WebAssign. The full disclosure, for the purposes of exams, including the final exam, I wouldn't bring this kind of question to an exam setting. This is more for homework where we have the extra time to actually run through it, not on a timed exam where we're kind of frantic trying to get the work done. And what makes this bad for an exam setting is part A right here. You'll notice we haven't done this a single time on these notes. We have never constructed a hypothetical table. But even if you're given conditional probabilities, you really can. And that's the hard part of this question right here. So this will help out with WebAssign when you see this problem. And first, well, we got to get through this block of text right here. It says, the paper action bias among elite soccer goalkeepers, the case of penalty kicks. So this was in the Journal of Economic Psychology in 2007, presents an interesting analysis of 286 penalty kicks in televised championship soccer games from around the world. So that's our context. I did us a solid here, in case you're not as great at sports like I'm not, if you're not familiar with how this goes. It says in a penalty kick, the only players involved are the kicker and the goalkeeper from the opposing team. The kicker tries to kick the ball in the goal from a point located 11 meters away. And the goalkeeper tries to block the ball from entering the goal. So that's great information, I suppose. Now they go off to say, for each penalty kick analyzed, the researchers recorded whether the goalkeeper jumped to the left to block, stayed in the center or jumped into the right. So they looked at what the goalkeeper did. And they also recorded whether or not the penalty kick was successfully blocked. So we have a lot of events. L, C, and R is what the goalkeeper is doing. We probably just want one color for all of those then. Let's go with maybe green. And B is the outcome of what the goalkeeper tries to do after he jukes left, right, or stays in center. Well, the kicker either threw a kick or kicked the ball that got blocked or didn't. So this is more about the kicker right here, I'd say. So we have 4 different events. Now they go off to say, based on their analysis of penalty kicks, the authors of the paper gave the following probability estimates. That's a lot of information, and kind of that's what's nice about probability as well. You could be given tons and tons of information like this, but now if you stitch it back together in just the right way, you can ask and answer very interesting questions based off of all this kind of information. It says right off the gate, use the given probabilities to construct a hypothetical 1000 table. So let's give this a try right down below here. I think this will be a good screen to settle it to. We've got our probabilities. I'll keep these in green. But now for these values right here, these are all conditional probabilities. That's what's making this table really kind of brand new for us. We still will start out the same, 3 horizontal line segments. We'll make them a little bit extra long this time. And in these 3 horizontal line segments, I want to first place the event B, that the kick was blocked. We can place it here, and then here with a complement, and then down below will be a total. So we'll start off this way. Now, next, we're going to have several columns this time, so let's just build this as we go. There is L for when the goalkeeper went to the left. There is C for when the goalkeeper stayed in the center. And there's R for when the goalkeeper jumped to the right to block a kick or attempt to block it. So now we need a total. 1000 goes right here, since it's a hypothetical 1000 table. And this is definitely a start. We can work with this and start placing down values. First values that are easy to place are these ones. And this is the only way we've done it up to this point in the course. We only put down values from a hypothetical 1000 table, when they were kind of ordinary probabilities like these, either a single event or an intersection or a union event. So these go not too bad. Let's work this out in the margin. Take 1,000 times probability of L, and we get 493. This goes into the column total under L. So right down here is 493. And keep on doing it. 1,000 times probability of C is 63 this time. So 63 goes under C. And one more time. And if you feel like you've done this a lot, and you don't want to write 1,000 times the event, and you're just putting the number 444 right here, that's completely fine as well. I usually take these extra steps of writing 1,000 times probability of R, only so that this is readable when you come back to the notes. You'll know why we got that number, where it even came from. This is 444, so it goes under R into that location. So we've completely finished off all of our ordinary probabilities, but now we need to deal with this stuff, the conditional probabilities. So this is where it all gets a little bit new. It's not too bad, just a new method. Any questions at all, folks, to this stage? Okay. I'll put here, this is the new stuff. In order to find what goes right here, this is my next main objective. Put in a value, we just about have it. Probability of B, if B and L are independent, I would just put 142 right here. But we don't know that. We would have to calculate to know for sure. So what I would do is take probability of B given L. Let's use this color right here, since this is going to look unusual. And we're going to multiply it not by 1,000, because when you see this particular conditional probability, it first says given L. That means none of that matters. We only care about L. That's how we've worked the tables before when we were dealing with conditional probability. Now, the only thing that matters is the count of 493. That's the only number on the table when you focus on that conditional. We take that 493 and we multiply it against probability of B given L, which means we're just multiplying 493 by 0.142. Let's write that in as a step, just so it's visible. 493 multiplies 0.142. We're going to get a count which may not be an even integer, but this says round to the nearest integer just for this kind of scenario. So let's see what we get. 493, multiply it by 0.142. And we have a count of, to the nearest integer, this would be 70 such kicks. So 70 would go right exactly here. Does that make sense to folks so far? Awesome. So we have 70 block ticks. Now we can solve the value right under. We'll just take 493 minus the 70. So that'll be 423. And if we were to try to practice calculating probability of B given L again, I'll erase this in a moment. This is what it would look like. It's kind of like a check in the middle, just to see, is our logic even sensible here? Probability of B given L goes like this. You count the total number of ways L could occur, 493 in this table. Count the total number of blocks, that's 70. Now, if we take 70, divide by 493, notice in the calculator, it seems like we're reversing this. 70 divided by 493. We get a probability of 0.141 rounding to the 2, which we really are expecting. So if we do this interesting new number game, we're really doing that probability computation by the red dot in reverse, giving us that number 70 right here. Once we have it, we're now in really great shape to start. Well, we have to do it again, but we're in really great shape for solving the whole table at this stage. Any questions or comments at the moment, folks, to this stage? Okay, well, let's try this again. I want to focus on this probability right here. Probability of B, the goalie blocked the kick. Given C, the goalie stayed in center. Given C is the most important part, so I'll wipe out left right? And even the total. This is everything we care about right here for that conditional probability. So like before, take the 63, multiply it against probability of B given C. And if I were to have been looking at the clock, I'd realize we've got like 20 seconds. Sorry about that, folks. Let me rate this in as 63. Multiplying probability of giving B given C is 0.333. Looks like that was meant to be a third, but it was rounded. 63 times 0.333. And I would round this one to, how about 21? That's the nearest integer. So we'll say 21 kicks are what results right here. 21 goes into this location, and that means it goes to that location as well. Well, then we can take the 63 minus the 21 and end up at a 42. I think this is a good stopping point for us, folks. We'll have to come back here. Fill in the last two dots. Sorry, I should have been going either a little bit faster or slower to find a better stopping point for us today. But any questions or comments before we call it a night? Okay, well, have a great night, folks. We'll be right on this question when we come back on Tuesday. And I'll start bringing in some extra questions as well. We're just about done, so we'll probably review a little bit earlier as well, starting Tuesday as well.